Dear students, Assalamu alaikum. This is lecture 15 for Engineering Fluid Mechanics MEE 225. Today we are going to review streamlines, streaklines, pathlines, do an example to see what streaklines and pathlines look like, and also see how we can calculate the fluid acceleration, and in doing so we will also learn about what material derivative is. So we'll proceed further. This is the definition of streamline, pathline, and streakline that we had already discussed in a previous lecture. A streamline is a line on which velocity vector is tangent everywhere. Dy over dx is equal to v over u. That is the equation of the streamline, and we see that there is no time involved in this equation, so streamline is independent of time. So a pathline is defined as the locus of points traversed by a given particle as it travels in the flow field. So basically, simply it is a path taken by a full fluid particle as it travels in the flow field. So a streak line is defined as an instantaneous line whose points are occupied by all particles originating from some specific point in the flow field. So at every point we have a particle over here, and all these particles have originated from one location but maybe at different times. So a line joining all these particles that have passed through one specific location is called a streak line. Also, if the flow field is steady, streamlines, pathlines, and streaklines are all the same. They are only different if the flow field is unsteady. So we have an example that will help us understand streamlines, streaklines, and pathlines a bit more. The example states that a plume of steam leaves a smokestack at x is equal to 0 and y is equal to 0. The plume lasts for 3 hours. The wind velocity is given as v is equal to 10I minus 5j for first 5 hours and v is equal to 5I for next 5 hours. Show the streak lines of flow for t is equal to 5 hours and 10 hours. So we have to draw two streak lines. Then draw path lines for fluid from t is equal to 0 to t is equal to 10 hours for fluid particle that left xy 0 0 at t is equal to 0 hours. So we are being told that the steam is being released for 3 hours. We are given velocity for first 5 hours and then velocity for next 5 hours, and we are being asked to draw two streak lines at t is equal to 5 and t is equal to 10 hours. So first we say, okay, the first fluid or the steam particle, first steam particle that leaves the smokestack will go in the direction v is equal to 10I minus 5j. So with u is equal to 10I, it will travel 50 feet in the x direction, and then minus 25 feet in the y direction, as the point is being shown now on your screen. The last steam particle leaves at t is equal to 3 hours and it travels for 2 hours in the direction v is equal to 10I minus 5j. So in 2 hours it travels uh, 20 feet or 20 units in the x direction and minus 10 units in the y direction. So you can see the point appearing now on your screen. So joining these 2 points, we have our first streak line at t is equal to 5 hours. So to draw the second streak line, um, we consider the first streak line that we have already drawn. The first fluid particle that is there at x is equal to 50 and y is equal to minus 25 will travel with will travel with a velocity of 5 I in the wind, in the direction of the wind. So if it travels for 5 hours, it will travel further 25 units, and it will go to x is equal to 75 and y is equal to minus 25, and it appears now on your screen. So similarly, the last fluid particle that was there at x is equal to 20 and y is equal to minus 10 will travel to uh, x is equal to 45 and y is equal to minus 10, and now appears on your screen. So now we have drawn our streak line at t is equal to 10 hours by joining the two new points. Now for the path line, we know that the fluid particle that leaves at the origin xy00 at t is equal to 0 travels for first 5 hours in the direction 10I minus 5j, and it goes to position x is equal to 50 and y is equal to minus 25, and then it travels further for next 5 hours and it goes to position x is equal to 75 and y is equal to minus 25. So now joining these 3 points, i.e. origin, that is 0 0, and x is equal to 50 and y is equal to minus 25, and then x is equal to 75 and y is equal to minus 25, we have our streak line that is drawn in purple color that you can see in the figure. So we have drawn streak lines, two streak lines, and a path line that originates from the origin. Um, we can also draw streamlines. Here in the figure you can also see streamlines of steam particles after 5 hours. So we have drawn them for after 5 hours for next 5 hours, and you can see them on your screen. They start from the first streak line and end at the second streak line. Motion of fluid might be described with the help of velocity and acceleration fields of the fluid. Acceleration is also important because it is a parameter in Newton's second law, and we need to calculate it. Since velocity is a function of time as well as the position, um we expect the velocity to change with position and time both. To this end, we say that in order to calculate the total change in velocity, and we represent that by dv, that might be a small change, but it is the change in velocity due to the change in position and the change in time as well. So dv is given as partial change in velocity dava v over dava x into dx, that is partial change in velocity with respect to x into distance traveled along x. Similarly, dava v over dava y into dy plus dava v over dava z into dz plus dava v over dava t into dt. Acceleration, we know that acceleration is rate of change of velocity, and we represent acceleration a as a is equal to dv over dt, and we have already calculated dv, which is the total change in velocity, whether due to change in position or due to change in time. So if we divide that dv by dt, we will get the acceleration. So if we divide the last expression that we saw for total change in velocity by dt, we get this expression that you can see on your screen. In this expression for acceleration that is on your screen that you can see, dx over dt is the u component or the x component of the velocity vector. Dy over dt is the y component of the velocity vector, which we represent by a lowercase v, and dz over dt is the uh, z component of the velocity vector, and we represent it by lowercase w. So finally, we can write the acceleration in the form that you can see on your screen now. So the acceleration that we have just calculated has two parts. One is the convective acceleration and the other is the local acceleration. The term dava v over dava t that you can also see on your screen, and it is written as local acceleration. Um, uh, we will feel this acceleration if we just remain at a fixed position in a flow field and see how the velocity is changing with respect to time at that fixed position. Convective acceleration is the acceleration that we will experience if we travel along the flow keeping the time fixed, or if the flow field is, of course, in an accelerating flow field, the flow field is unsteady. But if we take a snapshot of the flow field and we note velocity by traveling in different positions, we will see this convective acceleration. So the acceleration that we have just calculated in the last slide is actually a vector quantity. Uh, It will have three components. If we talk about the three-dimensional space, AX, AY, and AC will be these components in X, Y, and Z directions, respectively. You can see them on your screen as well. Um, the expression that we last saw, or we saw on the slide earlier, can also be written in the shorthand notation as A is equal to uh, dv over dt, which you can just see on your screen, where in dv over dt, d is capital. The operator capital D over capital dt is called the material derivative or substantial or total derivative. And you can see that on your screen as well now. The expression that you can see for material derivative or substantial derivative on your screen is very similar to the expression for acceleration that we saw on the last slide as well. Um, Physically, a material or total derivative of any variable t represents the rate at which that variable t changes with time if one is moving along a fluid. Uh, this kind of description is actually Lagrangian description. One seems to travel along a fluid particle and experiences all the changes that are happening due to change in time and due to change in position with the fluid particle. For example, T could be temperature, and total change in temperature with respect to time in a flowing medium can be given by the material derivative or substantial derivative or total derivative as shown on the screen. In this expression for total derivative, the total derivative of a vector quantity will be a vector quantity, and the total derivative of a scalar quantity will be a scalar quantity. As we saw in the case of acceleration, that dv over dt, which was acceleration, came out to be a vector quantity, and we had three components of acceleration: ax, ay, and az. And similarly, dt over dt, which is the total rate of change of temperature with respect to time, uh, will come out to be a scalar quantity. Also shown on your screen is the operator v dot del that is used in the expression for dt over dt. So as an example, to study fluid acceleration and material derivative, we can see problem 4.33 from our textbook. The statement is on your screen and it reads: a fluid flows along the x-axis with a velocity given by v is equal to x over t I hat, where x is in feet and t in seconds. Plot the speed for x greater than or equal to 0 and less than or equal to 10 feet, and t is equal to 3 seconds. In part B, plot the speed for x is equal to 7 feet and t greater than or equal to 2 and less than or equal to 4 seconds. In part C, determine the local and convective acceleration. In part D, show that the acceleration of any fluid particle in the flow is zero. And in part E, explain physically how the velocity of a particle in this unsteady flow remains constant throughout its motion. So we are being given the expression for velocity, that is v is equal to x over t I hat, and in part A we are being asked to plot the speed of any fluid particle uh, for x greater than or equal to 0 and less than or equal to 10 feet, and t is equal to 3 seconds. So we have to keep the t fixed in expression for velocity and change x and draw the velocity versus x. So that's pretty simple and straightforward. You can see the graph drawn on your screen now. In part B of the problem, we are supposed to do plot the speed again, but this time we'll plot the speed versus time, keeping the position constant. So in the expression for velocity, put x is equal to 7 and change time between 2 and 4 seconds and plot the speed. You can see the speed being plotted on your screen. So for both the parts A and B, we have the plots. We can see that if we are traveling along the x, if the x is increasing, the speed is increasing. But if we are at a fixed location in x and the time is increasing, the velocity is decreasing. In part C of the problem, we are supposed to find the local acceleration and the convective acceleration for this flow field. We know that acceleration A is given as dava v by dava t plus u into dava v by dava x plus v into dava v by dava y plus w into dava v by dava z. We know that dava v by dava t is the local acceleration part and the rest is the convective acceleration part. You can see the calculation on your screen. Dava v by dava t comes out to be minus x over t squared, and the convective acceleration, which is in this case just u dot dava v by dava x, because dava v by dava y and dava v by dava z will be 0, comes out to be x over t squared. In part C, we are supposed to show that the acceleration or the total acceleration of this velocity field that we are being given, it will be 0. So we have already calculated the local acceleration and the convective acceleration, which you can see written as a log and a con over here. Both the accelerations are equal and opposite, so the sum of local and convective acceleration will be 0, and as a result the total acceleration will be 0. In part E of the problem, we are supposed to physically explain that how the velocity of a fluid particle remains constant in this unsteady flow field. This we can do with the help of plots that we have drawn in part A and part B. The explanation is also written on your screen. So uh, the figure in part A is actually for a constant time, where the time is fixed and we are traveling along the x direction and seeing how the velocity is varying. So if we are traveling along the x direction, we can see that the velocity is increasing. In part B, we can see that if we are at a fixed point in space, that is x is equal to 7 feet, and the time is increasing, the velocity is decreasing with time. So for the given velocity field, the local and convective accelerations are equal and opposite. and this gives a zero acceleration, zero total acceleration throughout the flow.